Welcome back. Today we're going to be looking at SciPy in Python.
And some people might want to pronounce this Skippy, but really don't. It's definitely SciPy. So what is it? Well, it stands for Scientific Python, and it uses NumPy underneath. And it can do a lot of stuff, even more than NumPy. So why will we use it and not just go with the NumPy library? Well, it has loads of optimizations, and there are some frequently used functions, so you don't have to reinvent the wheel or recode a specific algorithm. You can just use the built-in SciPy one, and that makes it a lot easier when you're creating big projects. And of course, it's open source, so you could even collaborate on the project. So let's go and see what it does. So if we look at this notebook, the first thing we're going to do is install SciPy using pip. And if we wait a bit, you'll see that I've already got everything installed. But the exclamation mark at the top says this isn't Python code, so don't run it as Python. And you can see that it's installed pip. So the thing about SciPy is it has lots and lots of submodules, and you never use SciPy itself as a module, you just use the submodules. And so you generally say from SciPy import and then submodule. And if we look at the constants submodule, you can see that there are loads and loads of constants. So if we start by looking at some distance ones, you'll see there's an inch, a foot, a yard, a mile, and then some larger ones, so an astronomical unit, which is a different distance from the Earth to the Sun, a light year, the distance light travels in a year, and a parsec, 1 arc second for an astronomical unit. And if we run that, you can see we've got all of these different units. They've also got some maths ones, so pi, the golden ratio, and e. And you actually notice that e isn't the e you expected. You can't actually get that through SciPy. This is e that is the smallest value a float can store. They've also got some physical constants, and you can see each of them have two names. So c is the speed of light, h is the Planck constant, g is the gravitational constant, e the elementary charge, Na is Avogadro's number, k is the Boltzmann constant, sigma is the Stefan-Boltzmann constant, and then they've also got the mass of an electron, the mass of a proton, and the mass of a neutron. And you can see it's printed out each one twice. They've also got physical constants, so if we look at these, you can see it's got this value, which is repeated, so the gravitational constant. It's then got the SI units, and then it's got this, and this is the uncertainty. So if you ever did calculations, you might want to know the uncertainty, and you can get that using the physical constants object, which tells you a wide range. They've also got SI prefixes, so you can see them going in powers of 10, all the way from iota down to zepto. They've also got masses, so you can see a gram is 1,000th of a kilogram, and then the imperial ones, ounce, pound, and stone. Another thing we're going to look at is solving this equation. So we've imported NumPy, and the reason for that is if we do numpy.cosx, we could put in a NumPy array or just a scalar, and it will work out the whole thing. And so we're going to print what happens when we put in -1 and 1. And we can't put in 0 because we're dividing by 0 here. And you can see we get these two values. But what if we wanted to solve the equation? Well, I think that would be very difficult. But we can do that using SciPy. And we've imported NumPy again, although that's not really necessary. We've got this magic line, which means that we can display plots in the notebook rather than opening a new tab. X is a linear space, so it's just a set of NumPy values from -10 to 10. And Y is the equation of X, so it will apply the equation to each of the values. And then here we're just plotting X against Y and moving the axes around. And you can see that the graph looks something like that, which would be horrendous to solve. You can see there's a root there, and a few others. So what we can do instead is we can import SciPy.optimize and have a root. And so if we start with -1, then it says the iteration is not making good progress, so it's not improving. It's not certain why this is the case, but it's telling us that the method it's using isn't working. So instead, we could try from 1, and you see if we run from 1, then it says the solution converged, and the x value it got was this, so that's probably there, and it's told you a lot of different other values, and it took 10 iterations. Another thing we could do is we could minimize an equation. So if we look at this quartic and put in -1, 0, and 1, you see we get 1, 1, and 5. And then we could plot this, and you can see it looks something like this. So we're finding the root, probably somewhere over here, is quite difficult. But if we start at 0 this time and try and find a minimum value, you can see that it's managed to optimize it, taken 14 iterations, and it's found this value. So you can see that SciPy can do a lot of cool stuff. There are loads more, and some of them require a very complicated math to explain. I mean, even these were not simple, so I'm not going to go into any more. But it's something great to play around with. If you're ever doing a math problem or a data science problem, SciPy is probably the module you need. And hopefully you've enjoyed this video, learnt about a new module, and I'll see you again, same time next week. Till then.